So good afternoon, guys. So I know the first session after lunch is always difficult for students as well as for instructors, but we'll try to make sure that the session is engaging and interesting. So, you guys are able to hear me fine, right? Yes. Okay, good. So my name is Partha, and I'm from PayPal. So today, along with myself, I have two more colleagues, Mahesh Balan and Satish. Um, the plan for today will be giving you an overview of deep learning. Um, Covering the entire deep learning in 3 hours of time is a near impossible task. So the goal of this session is mostly to kindle your interest towards deep learning, just to show you what deep learning can do. Okay, so that's going to be the agenda of this session. So before we proceed, all three of us are alumnus of this institute. We graduated a couple of years back, so it's really good to be back to our alma mater. But this time we are not a student, we are as instructors, so it really feels good. So with that background, we can get started. So before we start, just a quick pulse check. So how many of you guys over here have some exposure to machine learning and deep learning? Have taken? Okay, fine, yeah. So have you guys taken it in your coursework, or? Okay, that's good. So you must be in your third year then. Degree level. Okay, good. Okay, fine. So since majority of the audience are not aware of deep learning, we'll try to keep our discussion at a very high level. Okay, so as I said earlier, the goal of this session is just to kindle your interest towards deep learning. Okay, we won't be covering the nuts and bolts of the topics that we will be seeing today. So the plan for today is I'll be getting started with computer vision, and then I'll hand it over to my colleagues who will be covering the second pillar, which is the NLP. So there are some technical challenges because of which we are not able to use this wacom board. So I had to use my laptop. So there are some delays. So sorry for that. Cool. Okay. As you may be knowing, when we talk about deep learning, there are two main pillars, as I said before. One is the computer vision, and second one is NLP. So computer vision is all about working with images. So when we look at the formal definition of computer vision, so computer vision basically it's the field of artificial intelligence, whereby we enable the computers to derive meaningful insights from some sort of visual input. That could be images, videos, or whatever, some visual clue. So that's the crux of the computer vision. So if you see the computer vision, it has grown tremendously in the past couple of years, and there are two main reasons for that. The first reason is, or the first thing which powered the growth of computer vision is availability of good quality data. So as you might be knowing, for you to train any AI based solution, the fundamental key ingredient is access to good quality data. Okay, and a couple of years back, not many of us had smartphones, but if you see now, it's very difficult to find a person who is not owning a smartphone. And with this smartphone, we are basically collecting a lot of data. So big tech companies, they have access to plenty of good quality images, which they use for training their ML models. And the second aspect which powered the growth of deep computer vision is availability to good quality compute. So working with images is not as simple as working with structured data, tabular data. It consumes a lot of CPU and memory for you to crunch images and videos. So for doing that, you need sophisticated hardware like GPUs. So a couple of years back, GPUs were not accessible by everyone. It was not something that anyone could easily access. But now with the advent of cloud, anyone could just simply start a server in EC2, I mean in AWS or GCP, and get access to GPUs. And also if you see, the computers also become really cheap. The the power of my, like the power of the smartphones that we have today is much, or I should say, it is as good as the powerful computer that was around a couple of decades ago. So because of these two main reasons, we saw a huge growth in computer vision, and the reason also holds good for like NLP. So so when we talk about the computer vision, so as I said, it's all about working with images. So I'm a fan of Dhoni, so I've just taken this image here. So a human eye, so basically when we look at an image, it is able to perceive the color, texture, and is able to process the image, and we are able to see it visually. But when we want to convey this information to a computer won't understand color, gradients, and things like that. So all it understands is just numbers. So if you want to convey an image or like represent an image which can be understood by a computer, all you can do is you have to just code it as matrices. Okay. So typically when we talk about image like representation, there are two modes in which you can represent an image. The first mode is called as RGB. So let's assume that this image is having okay, fine. Okay, so let's assume that the length of this image is 20 pixels and the height of this image is 15 pixels. Okay, so like roughly speaking, so you can represent this image with a matrix of size 20 cross 15. So there will be three matrices. Okay, one matrix for representing the red channel, one for green, and one for blue. And the reason why we have picked red, green, and blue is primarily because these three are called as the like primary colors. So with a linear combination of these three colors, you can basically like generate any color out there. And these values will be like ranging between 0 to 255. 255 being the highest intensity or brightness of that particular channel, and like 0 being no intensity of the channel. So like this kind of a mode will work fine when we are trying to display images on a digital board, be it laptop, your mobile phone, and things like that. But when we want to display color on a printed material, like your newspaper, like magazine, then we switch to what we call as CMYK, cyan, magenta, yellow, and black. But again, yeah, that's outside the scope of this, and we don't need to care about it much. I just want to give you some information on how to or how images are represented like in general. And like videos are nothing but collection of like images. So typically in 1 second we have close about 32 frames. Like of course like higher frame rates are possible, but 32 is what people standard like generally use. And yeah, please feel free to stop like now and then if you have any questions. Okay, like it's not that you have to ask the questions only towards the end, but yeah, feel free to like stop now and then. So what we'll be doing next is I'll just try to give you the different problem frameworks that are available out there in computer vision. Okay, we'll be looking at like what are the different like problems which we could solve, and frameworks that are available which can be used for solving problems using computer vision. And also we will see like real life examples as to how these frameworks are used in like in real life. So the first problem that we will be looking at is like image classification. So this is a very I should say a hello world of computer vision. Okay, so people who are into like programming, like you might know that you start when you start learning any programming language, you start by learning how to print hello world. Okay, so the equivalent of that in computer vision is image classification. Okay, so the task here is really simple. Okay, given an image, you want to classify to one of the buckets. I mean, there could be n number of classes that you're interested in. So in this case, let's say that you are having a model that classifies whether the given image has a cat in it or a dog in it. So that's a very simple like framework. So given any image, you classify to one of those buckets. It's not the case. I mean, it's not that always you have two categories, cat, dog, or A or B. It can be n number of categories. But the catch here is the prediction that you will be making will always be from the set that you have defined. You just cannot predict something that is outside the set that we have defined earlier. So that's the thing about like image classification. And the next like problem that we will be looking at is object detection. So sometimes what happens is we may not be only interested in knowing what is present in the like image. Let's say like sometimes like you might also be interested in where exactly in the image the object of interest is located. Okay, for example, here if you see, you have a like you have some dogs, and you also have a cat here. So here if you just try to have a cat dog classifier, it may not solve your problem, right? Because this image has a cat in it and also a dog in it. So like, what will the model output? Will it output a cat or a dog? Both are correct, right? So in order to handle this kind of like problem, we resort to this framework called object detection, whereby you try to locate where exactly in the image every object is present. You try to draw a bounding box. So this is what we call it as a bounding box. The square or rectangle, whatever you see, like is what we call it as a bounding box. And this is pretty much used in the like development of autonomous vehicles. Okay, we'll also see another like, use case of autonomous vehicles, a project which I had worked on personally. But yeah, so object detection is widely used in developing computer vision enabled modules for autonomous vehicles, just to detect what is there in front of the vehicle, because this is fundamental in driving a car, right? Like if you're developing autonomous vehicles, the car should be in a position to understand its surroundings, and you need to have something like object detection to do that. But there is one drawback to this. Okay, I wouldn't say a drawback. There are certain cases where this will fail. Can you just think of a case where this will fail, or I shouldn't call it as it will fail. There are few cases which this framework will not address. Can you just think of the framework which this problem framework won't address, or there is something like redundant here which we can do it slightly better? If you see, like object detection is a development of image classification, because like the image classification had some drawbacks. We want to fix the drawback, so we did object detection. There are few drawbacks like here as well. We need to fix it. That leads to the next like problem framework. Can anyone think of what could be improved here? Yeah, that's fine. But here, like if you think about it like from a fundamental perspective, there are few pixels which are not exactly dog but are marked as dog, because if you see here, all these pixels in here, they are not actually dog, right? They don't belong to a dog. Basically, if you just want to draw I mean cut out a dog, it's this exact boundary. So this rectangle is nothing but an approximation of a location of a dog. It's not the exact location. There are many pixels inside this box which does not belong to a dog. If you, for example, if you look at the pixels over here, they don't belong to dog. But from this like algorithm, you basically like you're classifying those pixels also as dog. So to address this, we go to the next like framework, which is called as the semantic segmentation. Okay, in semantic segmentation, we try to address this issue. Okay, where we try to do a pixel level classification. Okay, but here the catch is we won't be able to distinguish between different instances. Like sometime back, like you were mentioning, right? Like there are two different cats or dogs. Like why not put the same color to that? So like semantic segmentation basically is like is a framework where we will be able to do a pixel level classification. We will be able to exactly do a cutout of the object of interest, but if there are multiple instances of the same object, we won't be able to distinguish them. We will be just trying to put them together. So that's
How do you how do you distinguish between at a pixel level, in the sense that how do you know this pixel belongs to a dog and this one belongs to a cat?
yeah. So that is like that happens during the model training. So like in the training data, like whatever you have, you need to do the like labeling. Of course, like you won't be doing pixel like at pixel level. There are many like intelligent tools which will allow you to select the object and then give a like label to it. That happens during the
So this will be mainly a deep learning network.
yeah.
So where the network will learn through multiple inputs as to
Yeah,
what the pixel is. It is not
yeah.
just a matter of looking at the color or
No,
anything.
no, no. Like just a, like not a matter of looking at the color. Like if it has been just a color, then you can just like set some rules, right? if, because like at the end of the day, these pixels are nothing but numbers, RGB, like 3 numbers. So you can just like set some rules and get the value of as to what class that pixel belongs to, right? That's not the case. So here if you see here, there are two like pedestrians or cyclists, but both of them are put in the same packet. And one more thing to note here is, I mean, as we go forward, the complexity of the problem also increases. I mean, like image classification is the simplest problem. Like it is not very computationally like intense. Next, object detection is slightly intense, and this is much more intense. Okay. Again, the natural extension of this would be to do pixel level. I mean, to do like distinction between different occurrences of the same object. So that's what takes us into the next framework, which is instance segmentation. Okay. So here in instance segmentation, we will be able to I mean clearly say, I mean like clearly, like I said, every instances. Okay. Of course, you could let's say like there are two cats and one dog in this like image. You could put all the two cats in one category and then the dog as other category, or you could just do it instance level. Every instance can be given a different like color. I mean like these are like modeling details, but the idea is this. In instance segmentation, you will be in a much more better state. And this is heavily used, and this is also used in I mean like autonomous cars. So when you have a like camera like fitted in front of the car, you need to like detect what is called as a like drivable area. So like there are like roads and then like there are pedestrians like pathways, right? So you should clearly do a pixel level classification as to which all pixel belongs to the road, and which all pixels like don't belong to the road, like so that your car will just stick to that like drivable area. So that's one of the applications of instance segmentation or semantic segmentation. So that's about instance segmentation. So any questions so far? Are we all good? Okay, good. So the next thing that we'll be looking at is like video classification. So for certain problems, you just cannot work with images, right? So from this image, like can we say if the person is jumping or like or running? We can't, right? Just with one pixel. I mean, we need to analyze how these pixels or how these images changes with respect to time. So there is a temporal aspect to this. So we are into this framework of doing video like classification. So this video classification is very similar to like image classification, just that we will be accumulating as to how this, or we'll be accumulating the model's results as to how this changes with respect to time. So like as I mentioned earlier, the videos are nothing but I mean stacking of images. So you stack images one by one, and then you will be able to like do some analysis like on top of it. So I mean when we talk about the networks that are able to capture this temporal aspect, like there are things called as like LSTM, long short term like memory networks. So these networks are able to, or they are capable of capturing this temporal aspect like in the data, and we will be able to do this classification as to what activity the person is doing by looking at the video. And next we are into this generative modeling. So I mean like everyone is I mean the world is I shouldn't like I don't know whether it is happy or sad with the invention of ChatGPT, but yeah, that comes under the purview of like generative like learning. But generative modeling is not very new to like computation. Like it has been there for quite some time. So a few years back there was this app called Picasa that was famous, right, whereby you upload a photo and then you can do some like style transfer and so on and so forth, and all those things are basically from this generative modeling like framework. And as of now, if you see here like GPT-4 or DALI like E2, so these are the models which can generate an image for you given a text. Okay, so let's say you pass in a text like teddy bears working on new AI research underwater with 1990s technology. So the computer will automatically try to understand what the sentence is and will generate an image for you. Of course, like these are very advanced stuff. I mean I think GPT-4 is capable of doing this now, but I haven't tested it personally. But yeah, so that's about like generative modeling. Okay. So next we will move to something like interesting. So there are things like GANs, right? Like generative adversarial like networks. So like those come under the purview of computation. So the computation, like anything to do with images or videos, come under the purview of computation. So there's no strict definition. So the moment, like we say, like GPT-4, like GPT-4, people say like it's multimodal. It can work with text as well as like images. So you can put it under the umbrella of computation also. So since you're working with images, it comes under the purview of computation. That's all. Is it fine now? Good, right? Yeah, good. Okay, fine. So next we will like move into what is called as the like 3D recognition. So this is kind of advanced like, computation whereby we try to fuse information from multiple sensors. Okay, so there's something called as like lidar. Okay, so lidar basically helps us in detecting how far objects are by emitting some pulses. Okay, some radio pulses or something of that sort. So here when we talk about like use cases like autonomous vehicles, just a 2D detection won't work. Can you just tell me why a 2D detection won't work fine? Yeah, you won't be having the depth perception. Like 2D object detection will just only tell like what are all the objects in front of you, but it won't tell you how far objects are. Okay, so that information is missing. But when you're developing I mean a mission critical application like the vision system of a like autonomous vehicle, you need to account for these things. Like you just cannot tell the car that there's a like lorry in front of you. Like you just need to tell the car how far the lorry is, like, so that it can I mean adjust the gears or whatever accordingly. So that's where like 3D recognition comes into picture. So there are different ways of doing 3D recognition. The traditional way or the most common way of doing it is basically you have a like lidar sensor, and then you that's basically like a sensor placed in car, that like information is fused with the camera information that you have. So with these two information like together, you will be like developing a model which will be able to do 3D bounding box detection. Okay, it will not only give you a simple 2D box, it will also tell you how far the box is or how far the object is. So that will help you in taking more like cautious decisions. But if you like, I'm not sure like if you heard of this, like Elon Musk in his speech, he clearly mentioned that in Tesla, like the autonomous vehicles they make, they don't use like lidar systems. Okay, and like his justification was very simple. We are humans, we just have two eyes, right? We don't have a like a lidar sensor, but with just these two eyes which acts as camera, we are able to detect how far objects are. We won't be able to know the exact distance. Like I really don't know how far that camera is from me, but I like very well know that this person is closer to me than the camera. I'll be able to get that information with just my vision. I'm not using some kind of a like lidar like sensor. So I mean that's his way of like arguing, and he has mentioned that in his cars they are not using like lidar, they are just working with images. Of course, like the algorithms that they use to process and get the 3D information is much more like advanced. So that's about it. And the reason why they are not doing this is having a like lidar sensor in a car will increase the cost of the car. So they want to like reduce the cost, so they're just using or going ahead with images or cameras. I mean, like this information, this talk is also there in like YouTube. So in case if someone wants to know more about this, you can just Google about his thoughts on. But yeah.
But so Tesla, I mean, Teslas are quite sophisticated in the way that they navigate. In fact, so Teslas are quite sophisticated in the way that they navigate,
Yeah.
and they're able to do it without lidar, and lidar costs more.
Yeah.
So then, why do we have lidar? Shouldn't it be replaced with
So
Teslas?
yeah, that technology is not available with everyone, right? Only Musk has the technology to just detect the 3D objects with just images. The like traditionally people used to have the lidar sensor, and only with that they will be able to detect how far objects are. But like their technology is somewhat like proprietary, where they I mean they won't be able to do the same job which like lidar sensor will be able to do, but a very good approximation.
Uh, maybe this is not the right forum for the question. I'm just wondering why they have not commercialized the technology if it is so good. That would be a good validation of the technology as well.
That's correct, but I don't know. Maybe you should ask Musk. Maybe they lose the competitive edge. Yeah, I don't know. Okay, fine. So that's about like object detection in 3D space. Of course, this like use case is not only like limited to autonomous vehicles. It like can be used for any like 3D object detection. Okay, I've just taken the example of like autonomous vehicles, so it will be easy for you to relate to. But this application is quite wide. Okay, so next I'll be talking about a case study. So this is something that I worked on personally when I was with my previous organization. So this is basically we were working on like developing an driver state monitoring system. So like people are familiar with autonomous vehicles. There are 5 levels of like autonomy in like in an autonomous vehicles, starting from a level I mean level 0. Okay, you can consider it from level 1 to level 5. Okay, so level 1 is where you have very little like autonomy, and level 5 is where you have complete autonomy. Okay, so basically like in level 5 cars we don't even have the steering wheel. Okay, you can just like get into the car and it'll take you wherever you want to go, but we are not there at level 5. We are somewhere between level 3 and 4. So as you progress higher the levels, the more and more features will be there. So like at somewhere like in level 3, what we call it as conditional autonomy. So what I mean by this conditional autonomy is that the car will be able to handle most cases by itself. Okay, like it will be able to drive in most scenarios, but it is expected that the driver pays attention to the road. Like suddenly if someone jumps in front of the car, or if the like weather like deteriorates, the car may not be able to handle by itself in all cases. So it is expected that the driver pays attention to the road without losing attention. I mean, like it's also very common, right? Like if you are just sitting inside the car without doing anything, the chances of you getting distracted are really high. So basically we were tasked to develop a system whereby we just try to keep a camera in front of the like dashboard, and like do some analysis to check if the person is paying attention to the road, and getting distracted, or is fully focused on the road. So that was the task that we were working on, and this is a typical example of or I mean like computer vision can be used extensively to solve problems like this. So like I'll just give you a high level view as to how we address this problem, um, without getting into the details of it. Um, so typically if you see like in computer vision, there is this framework or this problem called key landmark like detection. Okay, or like landmark detection. So that is basically given any object, be it a face or whatever, you will be basically you want to get the positions, the pixel positions of the important parts or important pixels. Okay, so when you talk about a face, your key landmarks will be your jaw lining, your nose tip, your eyebrows, so on and so forth. So given a face, you will be in a position, or you want to get the pixel locations of all these like landmarks. That there are different, like few people classify, or they just like restrict to 10 landmarks. There are cases where they go up to like 100 landmarks. That depends on the compute power that you have. So the initial approach was to, given a face, we want to be able to get hold of all these key landmarks. And the reason why we don't want to work with the face as it is, because I mean it will induce a lot of bias. People with, let's say we trained it only on people with say fair complexion, like suddenly if a person with darker complexion like gets in, it may not be able to perform as good as it was performing on the other category of people. So we want to like get rid of all these sorts of issues, so we just used like landmark detection. So like given a face, we were basically extracting all the important like landmarks. So once we have the landmark, basically you can see this as feature engineering. Given a face, we were able to extract the important features. So you can see this as something like a two-dimensional, I mean an array, something of this sort, 20, 100, where this could be the x coordinate, this could be the y coordinate of the first landmark. This will be a second landmark, this will be a third landmark, so on and so forth. So depending on the number of landmarks that you have, you have this vector or matrix populated, and once you have that, we will be or we basically we were having I mean a classification module. So just like how we saw the image classification, there are like specialized networks that works on these coordinates. Okay, so technically we call these coordinates as point cloud. Okay, 2D point clouds or 3D point clouds, depending on which space you are getting these points. So once you have all these I mean like key points, we will be sending it to a ML classifier, which will just try to detect which zone the person is looking at. So we basically started off with 5 uh, I mean zones: left, right, like center stack, bottom and up. Okay, so like these were like predefined by us. So for any given set of features, we were able to detect or come up with a probability distribution over the output space, which is nothing but the zone in which the person is looking at. So for this given image, you can very well say that the person is more looking towards his right. Okay, so typically when we do a simple classification like problem, what we do when we have this kind of a probability vector of on a classification like problem, what exactly we do, like what will be the output of this? Anyone was taken MLDL? So what will be the output of this setting? Let's say that you have an input, you pass it to a network, you get this output: left 0.1, right 0.6. So these are nothing but you can consider them as probabilities. Okay, probability of looking at each zone. Okay, fine. So typically like what you do, you just pick that class that has a very high probability. So in this case, right has 60% probability, so we just pick that class. So for this given input, we just say the person is looking at right. That's the traditional way of doing this stuff. Okay, we just don't make use of or we just make use of only this value that corresponds to the highest probability, and we just chuck the remaining. But here we want to do something that is much more advanced. So we just took this probability vector as it is, and then we had our own like proprietary algorithm, whereby we just take the entire probability vector as it is and with some Euclidean geometry trick to come up with an attention score. Okay, again this is not so like straightforward, right? Because like sometimes people might argue that like looking at some like some other direction, left or right, for 1 second, like someone might say that that's fine, like that is not getting distracted, but when it exceeds 4 or 5 seconds, you call it as like distraction. But sometimes even for 1 second, people say that's getting distracted. So we didn't have a very solid definition of what, or we don't have a solid definition of what it is to be distracted. That's a very like subjective call, right? So we arrived on a like definition, and with the definition we were able to work it out, and we were giving something like an attention score, and we had certain rules which says that if the attention score goes below a certain threshold consecutively for 5 or 6 seconds, then you need to flag it. Basically you need to give an alarm inside the car that the person is like losing attention. So this is the problem that we worked on. Like there are many works along this line like in online. You can just like look it up. You'll find hundreds of like literature around this space. So any questions like so far?
Can we call it a logistic regression problem if we are just trying to figure out, based on the probability what's going to happen?
Yeah, I mean like logistic regression, like the idea is same, but logistic regression is a very simple model. Here we use something called as point net. So that's an architecture that is available like in deep learning, that is specialized to work on point cloud data. So whatever data that we got here can be seen as two-dimensional point cloud data. So these are points in space, right? You can see this, like see them as point cloud, and we had like separate like architectures that are suitable to work on this point cloud data. But the idea is same. Yeah. Yeah, like definitely, like that's a good question actually. So so like these types of models have to be calibrated for every car. So every car we need to fix the camera position first, and we need to make sure that the camera position won't change. So like these are inbuilt, right? Like it comes with the car. Like you can't change the camera. It's not like a camera that you go and place it once the car is built. So when you're manufacturing the car, the camera is placed in between. I mean, it's placed inside. But I mean, like an algorithm, what works for one car may not work for other car. You need to tune it for that particular camera position, and like a lot of calibration has to be done. Cool. Okay. So yeah, I do have some demos, but I'm not sure if I will be able to like show that because there are some technical challenges. But I'll try to do as much as I can. Okay. Cool. So. So before we proceed further, we'll just quickly see how I mean computer vision models are generally like evaluated. Okay, so we won't be looking at every model out there. I mean like every framework that we like saw. We will be just looking at image classification and object detection. Okay, fine. Like before I proceed, I just want to talk about some of the challenges here. I missed it. So here, when you build systems like this, there are two challenges. Okay, first is whatever computation that we are doing has to be done inside the car. Okay, it should not be the case where you place a camera like inside the car, you take the data out to some server, do the computation over there, and send the result. There are two challenges for when you do that. First is it brings in a lot of latency. So what if you drive through a forest where there is no network coverage? Your system won't work. So whatever like algorithm you design have to be run inside the car. So basically this can be seen as edge computing. So the users cannot have something super fancy which requires very high power. So like you need to keep in mind that you will be running this inside an edge device inside a car. So you won't be able to access super fast GPUs and things like that. And secondly, like privacy is like privacy concerns are there, right? Like you can't simply place a camera inside a car and then take the data to some server. That's a huge privacy issue. So you need to, whatever computation we do when we like perform these kind of like or when we try to solve these kind of problems, we need to keep this like this also in mind, like privacy aspect. So whatever data that is recorded in the car has to be processed in the car and it should not leave anywhere. So those are the two things. Yeah.
Could you give us a rough idea of the power of the edge device vis-a-vis some laptop or something, just to give us a rough idea of how powerful it is?
So I mean, so we worked on this. I mean, in 2019 or 2020, like I believe. At the time, this was basically consuming the power, which I mean, like the edge device that we were able to that we were trying to run on can be powered by a Raspberry Pi. Yeah, but of course it won't be as like sophisticated.
It's amazing that it can do all that.
Yeah. But yeah, like in the demo, like you'll see that like there'll be a lot of frames in which the detections will be missed. You won't be able to do this computation for every frame because of the computation challenges. But yeah, like NVIDIA is there. They are trying to work on like developing like state of the art like edge devices.
What if the driver changes the seat position?
Driver changes?
The seat position.
Yeah, like all those things can be like addressed using calibration. So like at the end of the day, these are like matrix multiplications, right? So if you know the exact seat position and if you know the exact camera position, you can do some kind of like projection mathematics and then make sure that they come to the same position in which it was trained from. So they basically some matrix multiplication that will bring it to the same position in which it was trained.
But the calibration should be in real time as well, while driving the seating position.
Yeah, like you won't be keep on changing your seat when you drive, right? You fix a seat and then you like start driving, right? So like before you drive, like depending on the position of your seat and the camera, the calibration will happen automatically. So all those things can be taken care of.
So do we use video or frame by frame for something like this thing?
This is actually like video, right? Like you just cannot like determine if a person is paying attention to the road or not just by looking at one frame. You need to see how the frame progresses with respect to time, right?
Yeah.
So this is actually like video analytics.
And you can complete these video analytics on a Raspberry Pi.
I mean, that's a good question, but then yeah, we did a lot of like you won't be able to place a very sophisticated camera here. The camera will also be something like a small camera.
Okay.
Like you can't like imagine the camera to be of this sort, whatever like we are recording here, and then process using like Raspberry Pi. Yeah,
Perfect. Perfect.
all those things
Thank
are
you.
there.
One question. Are sunglasses and face masks also a limitation to this?
Yeah, definitely. Yeah, like they are, because we use a lot of features that tracks the eyeball movement. To give an example, just to see if the person is paying attention to road and not feeling like drowsy, if you look at this point number 38, 42, like the distance between them is higher, what does it signify? Like the eyes are open. If the distance between them is low, which means that the person is like feeling sleepy or isn't, that's all. So yeah, so if a person is wearing like eyeglasses, then that becomes a challenge here.
There's no workaround for
Like there are workarounds. Like instead of using the regular camera, we can use IR camera, like infrared cameras. So instead of RGB, you can go in the IR mode. And IR also works fine in dark. So what if you're driving in a dark? Your like regular RGB camera won't work fine, right? You need to do something like heat sensing cameras. Yeah, so that was I understand. So the model has to be trained from different segments. So that was one of the issues that we had. So like, when we trained this model, this was done in collaboration with our team in the US. So the data collection was, I mean, like we were not able to use any publicly available like data because it didn't like satisfy our need. So we had to launch a data collection experiment, and that was mainly done by folks in the US. Okay, so they were like collecting data for us, and we were like building the model. Like everything worked perfectly fine. In the demo phase, everything was fine. But when we launched it as a pilot, we saw the model was performing really good for certain segments of people, and not that great for a certain segment of people. Like it turned out that the data collected was more from people with fair complexion. So that was issue, and later on to fix that, we just made sure that we just collected data that is representative of the population. We should not, so that's a issue with the data collection, right? So that's the important factor. So be it any like deep learning or machine learning model, like data is the key. You need to make sure that whatever data you are working with is not having any bias, and it should be representative of the population that you are working with. So yeah, like we can fix those things, like assuming that you have good quality data. Yeah, cool. Okay, fine. Yeah, I'll just quickly like skim through this in the interest of time. So yeah, so when we talk about evaluating a computer vision model, some of the evaluation is, or like pretty much they can be shared with the evaluation that we do on a regular ML problem, be it a simple classification like loan prediction like problem. So like image classification falls into that bucket, whereby you can use the traditional metrics like your precision, recall, or whatever to do this like evaluation. So here the evaluation is very simple, right? For every image you have a true label, and your model will be predicting something. So if they match, it's a correct prediction. If they don't match, it's a wrong prediction. So like that's all. So only with these two information you'll be able to say if the prediction was a true negative, or a true positive, or a false positive, or a false negative. Yeah, so you, this is what we call it as the confusion matrix. Okay, so this is pretty common across ML models. Yeah, so you guys are aware of the confusion matrix, right? What exactly confusion matrix is? Okay, no. Okay, it's fine, cool. Okay, maybe I'll just give a 30-second like overview. Okay, so let's say that there are two classes here. Okay, cat and a dog. Okay, for now we are assuming that cat is a positive class and then dog is a negative class. Okay, so if an image is actually containing a cat, and if you are correctly saying that it's a cat, then it falls under true positive. And the image, if the image is a negative, which is actually a dog, and your model is also saying that it's a dog, then it's a true negative. But if your image is having a cat, I mean basically yeah, like if your image is a cat and if you're predicting it as a dog, then it will be false positive, and if it's the other way around, it will be false negative. So that's the idea here. Okay, so for every image you will be able to, or for every prediction that you are making, you will be able to put it in one of these four quadrants, and you will be able to populate it. Yeah, but things get a bit challenging when we move to object detection, right? Because here the notion of correct wrong is bit I mean it's not very easily like understood. For example, let's say that you have a bird here, okay. The red box, so let's assume that the red box is the actual like ground truth, okay, whatever is there like in reality, and your model's output is the green one, okay. So let's say the model is drawing a box which is very close to the actual box, and this is also a case where the model is trying to draw a box, but like there's some overlap between the predicted box and the actual box, but it's not very significant compared to case 1. And in third case there is no box at all, the predictions is not happening. So here if you see like maybe the third case is like pretty much easy to understand, it's a as to why it is a false negative. But when you look at the first two cases, like how do you say a particular thing as like true positive? We define something called as intersection over union, okay. That is basically the region of intersection between the true box and the predicted box divided by the union of these two like areas. So this figure illustrates it quite well. So here the blue region is what we call it as the intersection between those two boxes, and here the blue is nothing but the union. So ideally if your I mean if your actual bounding box matches exactly with your true bounding box, I mean sorry like if your actual bounding box matches with the predicted bounding box, then what will be the value of IOU? 1, right? Yeah. So typically what people do is we set a threshold, okay. Typically the threshold is 0.5 or 0.6 depending on your use case. If your IOU is more than 0.5, you call it as a true positive, else it's a like false positive. So here the IOU turns out to be 0.96, so that's why it is called as a true positive here. And here the IOU is just 0.22, and that's why we call it as a false positive here, because the model is saying this region is the region where there is a bird, but that's not the region, so it's a false positive. So yeah, so like these are some of the metrics which people use for finding out or evaluating an object detection model. So any doubts on these two? Like I know that I kind of rushed towards the end, but yeah, I mean just to give you some flavor of how exactly evaluation is done on an object detection, that's what I want to do. Okay, any doubts on this? Okay, fine. So okay, so now what I'll do is I'll just try to show a quick demo. I'll try to show a demo. I'm not sure if everyone will be able to see it, but yeah, let's see, because there are some challenges in sharing the screen. Like that's why if you see I would have opened it only in the Chrome, not the PPT. So what I'm going to do now is I'm just going to run a simple object detection model which detects face of a person. So like you have seen the driver state monitoring, right, like some time back. So that was basically the starting point for this. So I don't know how to show this. Are you able to see it? Good. So you're able to see that it's detecting faces, but at the same time it's not very seamless, right? There are frames where the face is getting missed and things like that. That's because this is like it's using like my laptop's like hardware. Like it's not optimized for like running in this hardware. Just a very simple like network. I just want to show it as a demo. So this is what will happen when you do it in a like kind of like Raspberry Pi without like optimizing it. You need to do some kind of the floating point like conversion to integers to make sure that it runs optimally on that hardware. So this is something that I want to show, and the next demo, I mean like initially the plan was to project it there, but I don't know, there are some challenges here. Cool. So next we will see I mean yet another network. So whatever you saw here basically was like real time. I was just opening the camera in front of you and it was running fine. So now we will be looking at something which is much more like compute intensive. So we won't be able to run it on live. So what I'll do is I'll just try to record a video, like a short video, like 5 or 10 seconds now, and then I'll try to run the landmark detection. Okay, just to show you how it works. So why I'm running it offline is basically this won't be able to run on a real-time basis. This is computationally like much more like intense. So you should have basically I mean have like much more powerful hardware or optimize the code to make sure it runs fine. Just a minute. It's running. So for you to process a video of 10 seconds, it will take 20 seconds or more than that. So that's the reason why you can't do it like a real time on a real time basis. So you're able to see, right? This is something that I just recorded. So here you can see a dense 2D mask getting plotted here. So what I've done is I've just recorded a like video, and then I've just tried to run the first part of the driver state monitoring module, whereby given an image it will be able to give you the key landmarks. So here this is much more advanced one. So back then when we were working, we had only access to about 40 or 50 or 68 landmarks. So that was the state of the art back then, but now things have changed. There are even like 3D like landmarks that you can get to just with like images.
So I see that when you're turning your face, even the part that is hidden is being tracked. How is that possible?
That's a prediction, right?
Oh, that's a prediction.
Prediction, right? It's just going to predict where exactly that will, yeah.
It's rotating it. That's all.
Yeah. So yeah, so with that, I'm done with my part. So if there are any questions, let me know. We can take it up.
So, what are all the effects of a CV model giving a wrong output to a end user? So, for example, taking this landmark detection as an example, this is used for autonomous cars, as you mentioned, right? So, if it gives a wrong output that he is paying attention, then it is a danger for the
Yeah, it's a
end
failure.
user.
Yeah.
And if it warns him, alerts him too many times, that is also annoying, right? So,
Yeah.
how it is handled and how can you overcome it?
So yeah, so like developing a computer vision model for autonomous vehicle is not a very easy task. So it has to be approved by many government agencies and things like that. So it's not like a toy project that you're working on, right? So in case if this system fails, it'll I mean like a person's life is at stake. So those things, I mean, like these things will be well tested. So only if the authorities are convinced that the error which this system can make is less than a human. Like humans also like make accident, like we run into cars, we meet with accidents, right? So if the chances of this machine making a mistake is lesser than a human making a mistake, then these things can get approved. Basically we want to reduce human life loss, right? So yeah, so like these things will be put into like very strong testing and approvals. If there are no more questions, maybe I can hand it over to my colleague Mahesh to continue.